In the previous video, we talked about the concept of energy band, and based on the energy band diagram, we have seen that materials can be classified into three categories. That means the metals, which are also called conductors, semiconductors, and insulators. All right. So now, what are semiconductors? Okay, we are going to talk a little bit more about the semiconductors. Okay, and we're going to stick our discussion on this topic in this video. So basically, semiconductors are nothing but those solid materials whose conductivity and resistivity lie in between that of metals and insulators. Sorry, this must be between metals and insulators. Can I rub this off? Instead of conductors, this actually should be insulators. Okay. The conductivity of the semiconductors lie between 10 to the power minus 5 and 10 per ohm per meter, and the resistivity lie between 10 to the power 5 and 1 ohm meter. Okay, so we will discuss the types of semiconductors, right? Now there are two types of semiconductors. The first type of semiconductor is called the intrinsic semiconductor. The intrinsic semiconductor are nothing but pure semiconductors which are free from any impurity. Okay, and when we say impurity out here, we don't mean that the semiconductor must be clean, it must not be dirty, not like that. Okay, when we say impurity out here, we mean foreign substances, like it can be a foreign atom. Okay, as you can see in this first diagram, this is the crystal structure of the germanium semiconductor in 2 dimension. So you can see that it consists of only germanium atoms. Okay, and as we know, the germanium is tetravalent, right? Tetravalent means having 4 electrons in the valence shell. So you can see that these 4 electrons, as represented by the red dots out here, they form covalent bonds with the electrons of 4 germanium atoms. For example, this germanium atom out here, this electron form covalent bond with this electron which belong to this germanium atom. So this structure which I've drawn like this is actually a covalent bond. All right, I know that this is not the way you draw covalent bonds in chemistry, but here, just to give you the understanding of the structure, this is a covalent bond. It is not a double bond. Got it? So similarly, this electron which belong to this germanium form a covalent bond with this electron belonging to this germanium. Got it? So this is how the structure of the germanium, a pure germanium crystal, look like. Okay, and at 0 Kelvin, you can see that these electrons, they are inside the bonds. They are inside the covalent bonds. All right, that means they are trapped. They are trapped inside the covalent bonds. Got it? And the valence and the energy band diagram is shown here. So at 0 Kelvin, you can see that the valence band is completely filled with electrons, whereas the conduction band is completely empty, and the energy gap of germanium atom is 0.72 electron volt. Got it? Now what will happen if we raise the temperature? Let's say we raise the temperature. Okay, if we raise the temperature, then what will happen? The germanium atom will start to vibrate. There will be thermal vibrations of the atoms, right? Because the atoms now, they gain temperature from the surrounding. So these atoms will start to vibrate, and in that process, these bonds, they break off. Okay, breaking off of the bonds means these electrons now are able to free themselves, right? So for example, this electron here, it is now free. Okay, it is now free, this electron. It is now free, and where does this electron go? It goes out. It moves out. Let me use yellow. It moves out like this. Now this electron will come here. Okay? So this bond is broken now. From this position, the electron is free to move. Okay? It has escaped. So in the position where the electron was before, there is just an empty space or an empty seat out there. Got it? This empty seat is called a hole. Okay? And since the electron carries a negative charge, we can say that the hole is a seat of positive charge. Got the idea here? So that means that due to thermal agitations out here, the bonds got broken, and due to the breakage of the bonds, the electrons are free. They are freed from the bonds. So when this electron comes out here, it becomes a free electron. Got it? So now, this is what? This is a free electron. Understand? And where the electron was before, where the electron was sitting before, now that seat is empty, and that empty seat or vacancy is called a hole. A hole is nothing but a site or a seat of positive charge. Understand? So if we raise the temperature some more, we can say that more and more bonds got broken. Let's say this bond. Let's say this bond got broken, and now this electron will be released. It will come here. Okay? And in its place, what do we have? We have an empty seat or a hole. Got the idea or not? So if we look at the energy band diagram, these electrons, actually before breaking, where are the electrons situated? They are in the valence band. Okay? Now after breaking, that means these electrons have gained 0.72 electron volt energy at least. Or it can be more than that also. So what happened in the energy band diagram? These electrons now, they jump. They jump over to the conduction band. So now the electron will come here. What will be there here? Here, there's just an empty seat or a hole. Understand? So similarly, let's say this electron has jumped out here, has jumped there. So now the electron will come here. What is there in its place that it was before is just an empty seat. That means there is a hole. Is it clear here? So you got the picture here that in an intrinsic semiconductor, always electron-hole pairs are formed. That means the number of electrons in the conduction band, these are the electrons which are already freed. They are the free electrons. Okay? The number of electrons in the conduction band is equal to the number of holes in the valence band. So we can write Ne is equal to Nh. What is Ne here? Ne here is the number density of electrons in the conduction band, and H here is the number density of holes in the valence band. Is it clear? Now what will happen? What will happen if we apply electric field to this material? Let me take a new page. So let's say we have a block of germanium crystal, okay, and obviously this would be at not at 0 Kelvin, let's say at room temperature. So at room temperature we would have the holes, okay, the holes which are the sites of positive charge, and the electrons. Okay, we have the electrons like this. All right, and since it is an intrinsic semiconductor, the number of holes is equal to the number of electrons. All right, now if we connect this block of germanium with a wire to a cell, let's say, okay, and as soon as we plug in the key, what will happen is there will be electric field which will pass through the wire. Sorry, not through the wire, of course through the wire and also through the germanium. block. Okay, so therefore there will be electric field. Let me change the color there. So we have electric field this way, going from the positive terminal to the negative terminal. So what will happen now? These electrons will be attracted towards the positive end of the cell. Yes or no? So these electrons now, they will drift in that direction. They will drift in that direction. It's towards the left side. What about the holes? The holes will drift in that direction. Okay, so you can see that both the holes and the electrons are in motion, right? So the electrons, the motion of the electrons produces a current, electronic current IE, and the motion of the holes produces the hole current IH. The total current in the crystal is actually IE plus IH. Is this clear? Right, now the intrinsic semiconductor, it has some limitations. Okay, it has a number of limitations, and one of these limitations is that in a pure semiconductor, at room temperature, the number of intrinsic charge carriers is very small. The number of intrinsic charge carriers, that means Ne or NH, that is of the order of 10 to the power 16 per meter cube. That's quite small. Okay, so because of the small number of charge carriers, the semiconductor is having low conductivity. So that means its conductivity is low. It does not conduct properly. In a pure semiconductor, the intrinsic charge carriers are always produced due to breakage. All right, as I have explained before. How are these electrons and holes produced? They are produced due to breakage of the bonds, right? And you cannot control how many electrons will be produced just by applying heat. You cannot control that, right? So it's difficult to control the number of charge carriers in a pure semiconductor. And yeah, and for this reason, the pure or intrinsic semiconductor is not so much of use. Okay, it is not so useful in electronics. Got it? So what do we do then? How do we solve this problem? We solve this problem by a process called doping. Now, what is doping? Doping is actually the deliberate addition of impurity atoms to a pure semiconductor to increase its conductivity. Understand what is doping? Doping is the process of deliberate addition of desirable impurity atoms to a pure semiconductor to control its conductivity or to increase its conductivity. Okay, and the impure atoms that we use, it can be either tetravalent, sorry, not tetravalent, it can be either pentavalent, or it can be trivalent. Got it? And these impurity atoms added, they are called dopants. Okay, so what are dopants? Dopants are the impurity atoms that you add to an intrinsic semiconductor so as to increase the electrical conductivity of the semiconductor. Is that clear? There are methods how we dope a semiconductor. Okay, but I'm not going to discuss those methods right now. Got it? Okay. So because of doping, what happened now? We are adding impurity atoms. Then the pure semiconductor, it becomes impure. Yes or no? Now it becomes impure, right? So that impure semiconductor is called an extrinsic semiconductor. So what is an extrinsic semiconductor? It is a doped semiconductor or a semiconductor with suitable impurity atom added to it. Okay, so based on the type of impurity atom, there can be two types of extrinsic semiconductor. Let us discuss those. So depending on the type of dopant, the impurity atom, There can be two kinds of extrinsic semiconductor. Okay, and what are those? The first one is called the P-type semiconductor, and the second one is called the N-type semiconductor. Okay, let us discuss P-type and N-type semiconductor one by one. First of all, a P-type semiconductor. It is an extrinsic semiconductor formed by doping a pure semiconductor with trivalent impurity atoms like gallium or indium or boron or aluminum. Okay, so now imagine we have a pure germanium semiconductor as before. Got it? So what we will do here is, let's say we add a trivalent impurity atom indium, let's say. Okay, so let's say we add one indium atom, and then this indium atom will go and replace this germanium atom here, right? And what did I say? Indium is trivalent. Yes or no? How many electrons would it have? It would have 3 electrons. Okay, so that means this part here, there's no electron. It's just empty like that. There's a vacancy out there. Is this clear? So when you add one indium atom, what are you getting? You're getting one vacancy. One vacancy. And this vacancy is what? That is a hole. Understand? So if you add another indium atom, then you're getting another hole. So the more indium atom that we add, the more the number of holes. And holes here become the majority charge carrier. Okay, they become what? The majority charge carrier, because now the number of holes will be more than the number of electrons. Got it? And because holes are positive, that is why this extrinsic semiconductor is called a P-type. P for positive. P-type semiconductor. If you look at the band diagram of this semiconductor, let's say we have a conduction band here, and the valence band out there. Now what will happen? Initially, before doping, this is an intrinsic, yes, intrinsic, which is a pure semiconductor. Got it? So at room temperature, we already have the electron hole pairs, right? And we have the electrons somewhere here in the conduction band. The holes are in the valence band. Got it? Now the holes, these extra holes that are formed, okay, the extra holes that are formed due to the addition of the impurity atom indium out here, where do they lie? Where is their energy level lying in the energy band diagram? They lie in a level which is just above the valence band. Somewhere here. Somewhere there. So these holes are actually occupying this level. Okay, their energy is such that they are not fit to be in the conduction band nor on the valence band. Their energy is fit to be in this level out here, which is above the valence band. Got it? And this level out here is the energy. I mean the level is greater than the valence band range by 0.1 to 0.045 electron volt. So that means this gap out here is very small. Due to this small gap, the electrons which are present in the valence band, you remember or not those electrons which have not jumped over? Okay, there are still electrons which have not jumped over. Now these electrons are able to go. They are able to go from this valence band, and they will go and occupy these places out here. So now this electron will come here. In its place, there will be a hole. Understand? So let's say this another electron will go and jump and occupy this space out here. So this red dot will now occupy this space. In the space, in the place of this red dot, what is there? There will be a hole like this. So what is happening out here? This level is actually accepting electrons from the valence band. For that reason, this level is called the acceptor level. Got the idea? Right? So that is the P-type semiconductor. Okay. The N-type semiconductor, on the other hand, is formed by doping a pure semiconductor with pentavalent impurity atoms like arsenic, phosphorus, antimony, or bismuth. Okay, so what do we do here? We add what type of impurity atoms? Pentavalent. That means having 5 electrons in the outermost shell. All right, so imagine we have a silicon semiconductor crystal. Okay, silicon is just like germanium. It has 4 electrons in the outermost shell. Got it? So when you add a pentavalent atom, impurity atom, let's say arsenic, what will happen? This arsenic will go and replace the silicon somewhere here. So instead of silicon atom, now you have arsenic atom out there. And arsenic atom has got how many electrons? It has got 5 electrons. 5 electrons. So 1, 2, 3, 4, and 5 electrons out here. Do you see? So 4 out of those 5 electrons are able to form covalent bonds with 4 silicon neighboring atoms. But the 5th one is free. That is free. Understand? So that means if you add 1 arsenic atom, you're getting 1 free electron. If you add 2 arsenic atoms, you're getting 2 free electrons. If you add 1,000 arsenic atoms, you're getting 1,000 free electrons. So in this way, by adding more and more of the arsenic atoms, you're getting more and more free electrons. And more free electrons means more will be the conductivity. Got it? Now if you look at the energy band diagram, so we have this the conduction band, the valence band, and at room temperature already, due to heat, already we have the electron hole pairs. Yes, those are the electrons and these are the holes. Got it? Now this electron that is free and that comes along with the arsenic atom, where does it lie in the energy level diagram? Does it lie in here in the conduction band? No. Does it lie in the valence band? No. It lies somewhere here in a level which is just below the conduction level. Just like this, just below the conduction level. So you have the electrons, these electrons. Okay, so just one. I will draw many of them. I'm imagining that there are many of those free electrons. Understand? And this gap out here is also very, very tiny. It is, again, it's of the order of 0.045 electron volt. So it is very easy for these electrons, which from this level, to jump over to the conduction band to become conduction electrons, right? So these electrons, they go and they jump over like this. They jump over. So now you have more electrons in the conduction band. Understand? So when you have more electrons in the conduction band, then more will be the conductivity. Okay? And this level, it sort of like donates electron to the conduction band. For that reason, this level is called the donor level. Is it clear here? Right, so these are the extrinsic and intrinsic semiconductor.